Okay, let's do a summary of what you need to know for the test for DC circuits. So we're going to have some kind of voltage source. It's a battery of some kind. And then the simplest problem is I'm going to have one light bulb or one DC motor or one thing, just one thing. And we have voltage, current, and resistance. Oops. And those are the variables we use. And you need to know what these things mean. Now, current is a measure of how much charge is going by per unit time. So this is in coulombs per second, and a coulomb per second is called an amp. It's just how much charge is flowing through that circuit, through that wire. Now, by the way, you can have really high currents, like 5 amps or something, 5 coulombs per second. Now, remember when we shocked each other with the Van de Graaff generator? If I put 5 coulombs of charge on that Van de Graaff generator and you try to put your hand on it, it would kill you. 5 coulombs is a huge amount of charge for static electricity problems. The thing to remember is that in a wire, you don't have a net charge, right? You've got just as many protons as electrons in a wire. It's just that some of the electrons, the delocalized or the valence electrons of a metal, are allowed to flow. But the wires themselves have no net charge, and that's why it's safe. That's why you don't get lightning bolts coming out of your iPhone, all right? Because if you have any kind of current at all, it's a huge amount of charge that's moving. Now we also defined resistance this way. Okay, if you got voltage is how much energy is stored in a big basket of charge, joules per coulomb. It's how many joules per coulomb. Like if this is a 12-volt battery, every coulomb of charge in this wire is able to deliver 12 joules of energy to the world as it flows through that resistor. Now this resistor here can be an electric light, it can be a motor, or it could just be a plain old resistor designed to radiate heat and turn that energy into heat. Okay? And we defined resistance to say this: how much voltage do I need per unit of current? Okay, and we called that the voltage I need to get 1 amp of current to flow, we called that an ohm. 1 ohm. If something is 1 ohm, if you have 1 volt across it, you're going to have 1 amp of current flowing through it. That's how it's defined. But really, we take this and we define it, we call it Ohm's law. We say the voltage drop across the resistor is equal to the current flowing through that resistor times the resistance of that resistor. Okay? Now make sure when you're studying this that you're studying all the units. You know what ohms are, what coulombs are, what volts are in terms of joules and coulombs and time and so on. We also said that the power, the rate at which energy enters the circuit through the battery or leaves the circuit through the resistor is equal to the current times the voltage. If it's power in by the battery, this is the voltage delivered to the circuit by the battery, or it's the voltage drop across the resistor. Now, if you're dealing with resistors, we also showed that this was equal to I squared R, or V squared over R. Okay. Exactly. Now, if we had then we dealt with resistors in series. So anyway, on the test, you'll have a very simple circuit like this, 1 resistor in it. You have to solve for the current, you have to solve for the power, whatever, voltage drops, all that sort of thing. You'll have to deal with these, how much charge flows by in 10 seconds. You know, it'll be Pretty straightforward. But now we're going to get to this guy here. And just for fun, I'll put 3 resistors. But it doesn't have to be 3, and I didn't draw those resistors very well. Sorry. So we'll just call this the total voltage delivered by the battery. Let me move this over. We'll call this R1, R2, and R3. Now this is going to push current. We'll call that the total current. It's going to push current through those resistors. Now because they're in series, now visualize this. Think about current as being the flow of material stuff, electrons, through this wire. And if I've got 5 coulombs per second moving through here, I got to have 5 coulombs per second going through everything in that circuit. It's a steady current. Okay, so the total current is going to be equal to the current through resistor 1 is equal to 2 is equal to 3. Or if I put more in series, it's just equal to all of them, right? And hey, card people, if you need to quietly leave, you can do so now. And this will be on YouTube soon. Okay, but what about voltage? Look, voltage, this guy boosts this voltage up. This is 0, and we can indicate that by putting a little ground symbol here. This is at 0 volts. This has been boosted up. Let's say it's a 12-volt battery. It's been boosted up to 12 volts. As you go around the circuit, you're going to have a voltage drop here, and a voltage drop here, and a voltage drop here. So we can say that V total equals V1 plus V2 plus V3. Now, what is the total resistance of the circuit? I can combine this equation with Ohm's law. I'm not going to do this here because this is just a review, but we can say that the total resistance of this circuit is just R1 plus R2 plus R3.
Are you sure?
I am. Now, this right here, this is a total resistance. You can now use this to find the total current in the circuit by using Ohm's law, right? V total equals I total R total. So think about this. You can use this with Ohm's law to figure out the current. Once you know the current, and you know that the current is the same in all of these, you can figure out the voltage drops through each individual resistor and the power out each of those individual resistors. So you will need to do that. I'm going to give you a circuit like this, and you'll need to use these equations here to figure out what the current is, what the total resistance is, and what the voltage drops are through each resistor. And they should add up to the total resistance or total voltage. That's a good way to check your work. I'm also going to give you a parallel circuit. So here's our total voltage again. Okay, and so here's the total voltage. Here's R1, R2, and R3. And I can have more than 3 in parallel. Now, what defines things that are in parallel? What do R1, R2, and R3 have in common? Voltage man must make the same jump. If this is from here to here, it's the same voltage drop as from here to here, as the same as from here to here. Remember when we stretched out those aluminum foil strips? For those of you who are here for that, everything on this aluminum foil strip is at like, what do you have, 4.5 volts or something when you had 3 electric cells in series? So it drops down the same amount. And that's why if you open one of these up, these two don't care. They'll have the same voltage drop, same amount of current. So what we can do is say, look, V total equals V1 equals V2 equals V3. Now, what about current? Well, here's the total current delivered coming out of that voltage source, coming out of those bunch of batteries there. Well, look, some of it's going to go down this way, some of it's going to go down this way, and some of it's going to go down this way. But when I add up these three currents, it has to add up to the total current. The total current is going to be equal to I1 plus I2 plus I3. It makes sense. Don't just memorize this. Think about it. It has to be true. Then you can use this to combine with this. What's the total resistance? Well, each resistor you add in parallel to the others makes it easier for current to flow. It's going to add to the total current. Like if I put another resistor over here, doesn't affect these currents. I1, I2, and I3 are all going to be the same thing, but now I'm just adding I4. So that means that the total resistance of the circuit is going to allow more current to flow than was flowing before, which means there's less overall resistance. So the total resistance of the circuit is going to be 1 over R1 plus 1 over R2 plus 1 over R3. And your answer, your total resistance, will be less than your smallest resistor in parallel. So that's one way to check. And of course, stuff about power and all that, P equals IV for each one of them and so on. Okay, then, and that's, oh shoot, I'm not going to be able to do this on one sheet of paper. You're going to have a mixed circuit or a complex circuit. And that's very similar to the one that I gave you for the starter today. Here's R1. Then you'll have an R2, R3. Okay, and the way you think about these is here's the voltage. If you combine these into one, they're in series, so you combine them. Yep, R1 and this. Then you can figure out and then you treat these two in parallel so you can get the overall equivalent resistance. Then you can get the total current. Then you could just use all these little tricks that you learned before to solve the circuit. And we'll practice that in a little bit. But I do want to make, in the 3 minutes I have left, a quantity chart. Okay, let me zoom in. So we have the quantity, the variable, and the units. Quantity, voltage, V. Sometimes we use a delta V, sometimes a cursive E, but I'm just going to stick with V. Volts. Where's my other pencil? Volts, which is a joule per coulomb. I want you to know that. And we just abbreviate with V. It's the only quantity I know of where the variable and the unit are the same letter. Then we have charge, Q, coulombs, C. Time, T, seconds, S. Current, I, what is that current? Is it coulomb per second? Which is called an amp. And we abbreviate it with an A. Resistance, R. Now, resistance is an ohm with that little horseshoe thing. But remember, it's a volt per amp. An ohm is the same thing as a volt per amp. How many volts do you need to get 1 amp of current? And I think there's one last thing. Power P watt and just a W, and of course that's a joule per second. You can also think as a volt amp, because a volt times an amp, if you break those down into joules per coulomb and coulombs per second, the coulombs cancel, you're left with joules per second, which is a watt. So I did all get it all on one sheet of paper. Let me zoom out. The only thing that's really kind of incomplete here is that mixed circuit. So you just have to apply the lessons from these two to this one individually, and break it down to its little parts, and look at the starter problem that we did today. And I'll give you more practice next time. But this is what you need to know for DC circuits for the test coming up. And that is all.